Number one on the final, it's just going to be scrambled. So light is a special type of electromagnetic wave. It's got a electric component to it, and it's got a magnetic component to it, and I'm not doing a very good job, but these are at right angles to one another. So one goes up and down like this, while the other one goes side to side like that. Not a kind of sound wave. It's not mechanical. It can travel through empty space. All right. This is white light coming into a prism, and you have to be able to match up these letters with the colors. So these are all the colors, all the wavelengths of light from longest wavelength to shortest wavelength, and from least amount of bend to greatest amount of bend when we're talking about refraction. So when the light goes in and it refracts, the one that bends the most is violet. And the one that bends the least is red. And the others are in order. What wavelengths are combined to make black light? None, because black is the absence of light. When light travels from air into glass and bends, this is an example of refraction. So this is refraction, and reflection is when you bounce something off of a surface like that. And scattering is what happens to light when it comes into the atmosphere, and it kind of, certain wavelengths especially, like blue and indigo and violet, bounce all over the sky, and longer wavelengths like red, they just go right down to us. So when we're standing here on the earth, we see the longer wavelengths, and the blue we see all over the sky. So skies are blue. And at sunset, when the sunlight's going through a thicker amount of atmosphere because of the angle, all these colors can't make it to us, and just the red does. So sunsets look red. Now these terms relating to refraction and reflection, they are described relative to this thing called the normal. So if this is an incident ray just means, it's a ray that comes in and hits. This is the surface that it hits. We draw a thing called the normal right there at that surface, and the normal is a perpendicular line. So this is a right angle, this is a right angle, this is the normal. And the angle, all these angles are angles between the normal and the rays. So this is the incident ray. So this is the angle of incidence between the normal and the ray. And this is the reflected ray, and this is the angle of reflection between the reflected ray and the normal. And this is the refracted ray down here, and this is the angle of refraction between the refracted ray and the normal. All these other spaces over here, they're nothing. There's no name for those. We don't call those anything. The law of reflection states that the angle of incidence equals the angle of reflection. So this angle has to equal this angle. And so you wouldn't have anything like this. Light wouldn't come in like this and then bounce like that. Just doesn't happen. There's a law against it. All right. I've already kind of made a mess of this, but I can redraw this. Gonna erase, and then I'll draw all these things again. This, you can use Snell's law to do this, but I think it's a lot easier if you just think about little cars entering and exiting materials. So driving off the road, driving onto the road, that kind of thing. What you have to do is figure out how this ray is going to refract as it travels from air, which is out here, to glass, and how this one's going to refract as it goes from glass in here out to air. On the exam, I might switch it. I might put glass out here, and then there'll be an air bubble inside, so it'll be different, but you can still do it. All you need to know is where light travels faster. So we've talked about this. If you can't remember whether light travels faster through glass or through air, then you can jump down to the next one. A high index of refraction, means that light travels more slowly. So if you look at the indices of refraction here, air, its actual index of refraction is 1.003, and glass, it's 1.5. So a bigger number means light travels slowly. The one light travels the slowest in here is silicon, 3.5. Diamond is 2.41. So here's how I suggest doing this. Turn your paper so that you're looking along one of these arrows. So I'm looking along this arrow, and I'm going to extend the arrow, and I'm going to draw a little rectangle on it representing my car. And my car is going this way. And as my car drives, this tire, because of the way this is sloped, this tire is going to enter the glass first. And when it does, at that moment, the car is going to look like this. This is in the glass, this is out in the air. Now I'm going to draw a little arrow representing how fast each tire is going to go. The one in the glass is going to go slowly, and the one outside in the air is still going to be going faster. So if you do this, if you push something along and you slow down the right side and you speed up the left side, that's going to make it turn to the right. On the other hand, if you're coming out of the glass in a little car like this, as the car starts to exit the glass, it's going to find itself in a position where one front wheel is still in the glass and one is out. The one that's still in, that's the left one. That's the one that's going to go slowly. So there's my little arrow. And this is the one that's going to go fast because it's out in the air, like that. So if your right side goes fast and your left side slows down, that's going to make you turn to the left. Again, I've already been over number 13. Higher numbers here mean light travels more slowly. Lower numbers means light travels faster in that material. This one, have to figure out which one has a high index of refraction, which one has a low index of refraction. So we just need to figure out which one, in which one of these light goes more slowly. So we do the car thing again, except we're working backward. We're saying the car's going like this, and when it's transitioning from material A to material B, this left tire is in B, and the right one is in A. And it's turning to the left, which means this right one's going fast, and this left one is going slowly. So this material over here is a material where the light goes fast. And this material over here is material where light goes slowly. So this B has a high N, and A has a low N, which is what I wrote before. Low N, except it looked like lone, high N. Which one has a higher index of refraction? That's B. Was doing this one before, and for some reason punching things wrong in my calculator. So this first, well, let me read this. The speed of light through some substance can be calculated with this formula: V equals C over N. C is the speed of light in a vacuum, and there's the value, 3 times 10 to the 8th meters per second. So it's 300 million meters per second. Find the value of N. So we're looking for N for a substance in which the speed of light is this. So this is V, and we want N. So we have to rearrange this. And we can do the triangle. We've got 3 little variables here. So this is a simple situation. Sometimes we have things like F equals MA, and we know that since the M and the A are multiplied together, they go on the bottom. But here we're starting with the equation where V equals C over N. If C is on top, it's going to go on the top of the triangle. So you just put it there. V and the N go on the bottom. So we've got 3 formulas we could do here. We could do C, cover it up, is V times N. We could do N, cover it up, is C over V. Or we could do V, cover it up, is C over N. But we need N. So cover up N equals C over V. C over V. C is 3 times 10 to the 8th. V is 1.24 times 10 to the 8th. These 10 to the 8ths, they're 100 million. So since we have 3 times 100 million on the top of the fraction and 1.24 times 100 million on the bottom of the fraction, you can just ignore these. They cancel out. So all we really need to do is 3 divided by 1.24. And let's see if I can do this correctly this time. 3 divided by 1.24 equals 2.419, which comes out to about 2.42. So that's the value of n. Identify the substance using the table. So I just look at all my n's. I'm looking for 2.42. And there's 2.41. That's the closest. That must be it. Whoever made this, which was me, screwed up just a little bit, but that's the answer. So this is diamond. Diamond has an index of refraction of 2.41, which is the closest. Almost done with this section. Show what happened when rays of sunlight hit the 2 mirrors below. So I'm just going to use the law of reflection, but I don't know. This is a convex mirror and this is a concave mirror, and you shouldn't really have to use the law of reflection to figure this out. We've done this before. So this is just going to go hit this surface and bounce straight back, because if you drew the normal here, there'd be no angle of incidence. So there's no angle of reflection. So it's going to come straight back. This is going to hit here and bounce off like that. This is going to hit here and bounce off like that. And if you wanted to, you could draw the normal in between there. But this is going to make rays diverge. And this is going to do the opposite. This one will go straight back. This one is going to bounce this way. This one's going to bounce that way. It's going to make them converge. And down here with the lenses, we're going to have just the opposite. I guess I should tell you that this lens is glass and this is air. You can assume that with lenses unless I say otherwise. This one's going to pass straight through, and this is going to refract and converge, and this one's going to refract and converge also. So you can burn ants right there, or holes in paper. Now this is just the opposite. This is a diverging lens. So this is going to go through and go like this and go like that. You saw this when we did the laser ray boxes. Sorry about the sun. It's getting a little annoying.